Hello friends, welcome to our YouTube channel. An electrical network is called a two-port network when it comprises of one input port and one output port. Today we shall find when a two-port network is called reciprocal network. We shall derive the conditions for reciprocity for different sets of parameters used to describe two-port networks. Later, we shall take up a couple of numerical problems to learn how to check reciprocity of given electrical networks. Now let us first see when we call a two-port network a reciprocal one. A voltage source Vs is connected to the input port of the two-port network shown, and the output port is short-circuited through an ammeter. Therefore, V1 equals to Vs, V2 equals to 0, and I2 equals to minus I dash, because the output port current I2 and the short-circuit current I dash are flowing in opposite directions. Now let us note down the ratio of excitation voltage Vs and the response current I dash. Now the voltage source Vs is connected to the output port and the input port is short-circuited through an ammeter. Now we can write V1 equals to 0, V2 equals to Vs, and I1 equals to minus I double dash, because the input port current I1 and the short circuit current I double dash are flowing in opposite directions. Let us note down the ratio of excitation voltage Vs and the response current I double dash. If these two ratios are equal, then we can call this two-port network as a reciprocal network. Therefore, we can conclude that a two-port network is said to be reciprocal if the ratio of excitation to response at one port is invariant to an interchange of the positions of excitation and response. This equality gives us I dash equals to I double dash. Now let us first derive the condition for reciprocity for open circuit impedance parameters, or simply called Z parameters. When we describe a two-port network using Z parameters, we express the port voltages V1 and V2 in terms of port currents I1 and I2. The linear equations used in this case are V1 equals to Z11 I1 plus Z12 I2 and V2 equals to Z21 I1 plus Z22 I2. Let us now connect a voltage source Vs at the input port and the output port is short-circuited. Therefore, V1 equals to Vs, V2 equals to 0 and I2 equals to minus I dash, because the output port current I2 and the short circuit current I dash are flowing in opposite direction. From the second equation we can write 0 equals to Z21 I1 minus Z22 I dash. Therefore, I1 equals to Z22 divided by Z21 times I dash. Now from the first equation we can write Vs equals to Z11 I1 minus Z12 I dash. Now using the expression of I1 we can write Vs equals to Z11 into Z22 by Z21 minus Z12 times I dash. Or we can write Vs equals to delta Z by Z Z21 times I dash, where delta Z equals to Z11 Z22 minus Z12 Z21. Therefore, I dash equals to Z21 divided by delta Z times Vs. Now let us connect the voltage source Vs at the output port, and the input port is short circuited. Therefore, V1 equals to 0, V2 equals to Vs, and I1 equals to minus I double dash, because the short circuit current I double dash and the input port current I1 are flowing in opposite directions. The linear equations used to describe a two-port network using Z parameters are V1 equals to Z11I1 plus Z12I2 and V2 equals to Z21I1 plus Z22I2. As the input port is short-circuited, V1 equals to 0. Therefore, from first equation, we get 0 equals to minus Z11 times I double dash plus Z12 times I2. Or we can write I2 equals to Z11 by Z12 times I double dash. Now, V2 equals to Vs. Therefore, from the second equation, we can write Vs equals to minus Z21 times I double dash plus Z22 times I2. Using the expression of I2, we can write Vs equals to minus Z21 times I double dash plus Z22 into Z11 by Z12 times I double dash. Rearranging this equation, we get Vs equals to delta Z divided by Z12 times I double dash. Therefore, I double dash equals to Z12 by delta Z times Vs. We have already got I dash equals to Z21 by delta Z times Vs. For a reciprocal network, I double dash must be equal to I dash. Therefore, we can write Z12 equals to Z21. That is the condition for reciprocity for open circuit impedance parameters. Now let us derive the condition for reciprocity for short circuit admittance parameters, or simply called Y parameters. When we describe a two-port network using Y parameters, we express the port currents I1 and I2 in terms of port voltages V1 and V2. The linear equations used in this case are I1 equals to Y11 V1 plus Y12 V2 and I2 equals to Y21 V1 plus Y22 V2. Now let us connect a voltage source Vs at the input port and the output port is short circuited. Therefore, V1 equals to Vs, V2 equals to 0 and I2 equals to minus I dash, because the output port current I2 and the short circuit current I dash are flowing in opposite directions. Now from the second equation we can write minus I dash equals to Y21 times Vs. Now let us connect the voltage source Vs to the output port and the input port is short circuited. Therefore V1 equals to 0, V2 equals to Vs and I1 equals to minus I double dash, because the short circuit current I double dash and the input port current I1 are flowing in opposite directions. Therefore, from first equation we can write minus I double dash equals to Y12 times Vs. For a reciprocal network, I dash must be equal to I double dash. Therefore, we can write Y21 equals to Y12. That is the condition for reciprocity for short circuit admittance parameters. Transmission parameters are widely used in the field of power system and telecommunication system. Let us now derive the condition for reciprocity for transmission parameters. When we describe a two-port network using transmission parameters, or simply known as T parameters, we express the input port variables V1 and I1 in terms of output port variables V2 and I2. The linear equations used in this case are V1 equals to AV2 minus BI2 and I1 equals to CV2 minus DI2. Now let us connect a voltage source Vs at the input port and the output port is short circuited. Therefore, V1 equals to Vs, V2 equals to 0 and I2 equals to minus I dash, because the short circuit current I dash and the output port current I2 are flowing in opposite directions. Now from the first equation we get Vs equals to B times I dash. Therefore I dash equals to Vs by B. Now let us connect the voltage source at the output port and the input port is short circuited. Therefore V1 equals to 0, V2 equals to Vs and I1 equals to minus I double dash, because the short circuit current I double dash and the input port current I1 are flowing in opposite directions. Now from the first equation we can write 0 equals to AVs minus BI2. Therefore I2 equals to A by B times Vs. Now from second equation we get minus I double dash equals to CVs minus DI2. Using the expression of I2 we can write CVs minus D into A by B times Vs. By rearranging this equation we get minus I double dash equals to minus AD minus BC divided by B times Vs. Therefore I double dash equals to AD minus BC divided by B times Vs, or we can write I double dash equals to delta T by B times Vs, where delta T equals to AD minus BC. For a reciprocal network, I double dash must be equal to I dash. So we can write delta T, that is equal to AD minus BC, equals to 1. That is the condition for reciprocity for transmission parameters. For a symmetrical network, we know A equals to D. Therefore, we get delta T equals to A square minus BC equals to 1. So, if we know any two transmission parameters, we can derive the other two parameters easily. Like transmission parameters, inverse transmission parameters are useful in the field of power system and telecommunication systems. When we describe a two-port network using inverse transmission parameters, or simply called T' parameters, we express the output port variables V2 and I2 in terms of input port variables V1 and I1. The linear equations used in this case are V2 equals to A dash V1 minus B dash I1 and I2 equals to C dash V1 minus D dash I1. Let us connect a voltage source Vs at the input port and the output port is short circuited. Therefore, V1 equals to Vs, V2 equals to 0 and I2 equals to minus I dash. From the first equation, we can write 0 equals to A dash Vs minus B dash I1. Therefore, I1 equals to A dash by B dash times Vs. From the second equation, we get minus I dash equals to C dash Vs minus D dash I1. Using the expression of I1, we can write minus I dash equals to C dash Vs minus D dash into A dash by B dash times Vs. Rearranging this equation, we get I dash equals to A dash D dash minus B dash C dash divided by B dash times Vs. Or we can write I dash equals to delta T dash by B dash times Vs, where delta T dash equals to A dash D dash minus B dash C dash. Let us now connect the voltage source Vs at the output port and the input port is short circuited. Therefore, V1 equals to 0, V2 equals to Vs and I1 equals to minus I double dash. From the first equation, we get Vs equals to B dash I double dash. Therefore, I double dash equals to Vs divided by B dash. For reciprocal network, I double dash must be equal to I dash. Therefore, we can write delta T dash equals to A dash T dash minus B dash C dash equals to 1. That is the condition for reciprocity for inverse transmission parameters. If this two-port network is symmetrical as well, then A dash equals to D dash. Therefore, we can write delta T dash equals to A dash square minus B dash C dash equals to 1. If any two of the four T dash parameters are available, the other two can be easily obtained using this relationship. hybrid parameters are widely used in the field of electronics. Let us now derive the condition for reciprocity for hybrid parameters, or simply called H parameters. When we describe a two-port network using H parameters, we express the input port voltage V1 and output port current I2 in terms of input port current I1 and output port voltage V2. The linear equations used in this case are V1 equals to H11 I1 plus H12 V2 and I2 equals to H21 I1 plus H22 V2. Let us now connect a voltage source Vs at the input port, and the output port is short circuited. Therefore, V1 equals to Vs, V2 equals to 0, I2 equals to minus I dash. Now, from the first equation, we get Vs equals to H11 I1, and the second equation gives us minus I dash equals to H21 I1. Therefore, I dash equals to minus H21 divided by H11 times Vs. Now, let us connect the voltage source at the output port, and the input port is short circuited. Therefore, V1 equals to 0, V2 equals to Vs, and I1 equals to minus I double dash. From the first equation, we get 0 equals to minus H11 I double dash plus H12 times Vs. Therefore, I double dash equals to H12 divided by H11 times Vs. For a reciprocal network, I double dash must be equals to I dash. Therefore, we can write H12 equals to minus H21. That is the condition for reciprocity for hybrid parameters. Like hybrid parameters, inverse hybrid parameters are widely used in the field of electronics. Let us now derive the condition for reciprocity for inverse hybrid parameters, or simply called G parameters. When we describe a two-port network using G parameters, we express the input port current I1 and output port voltage V2 in terms of input port voltage V1 and output port current I2. The linear equations used in this case are I1 equals to G11 V1 plus G12 I2 and V2 equals to G21 V1 plus G22 I2. Let us now connect a voltage source Vs at the input port, and the output port is short circuited. Therefore, V1 equals to Vs, V2 equals to 0, and I2 equals to minus I dash. From the second equation, we get 0 equals to G21 Vs minus G22 times I dash. Therefore, I dash equals to G21 by G22 times Vs. Now, let us connect the voltage source Vs at the output port, and the input port is short circuited. Therefore, V1 equals to 0, V2 equals to Vs, I1 equals to minus I double dash. From the first equation, we get minus I double dash equals to G12 times I2. From the second equation, we get Vs equals to G22 into I2. Therefore, I double dash equals to minus G12 divided by G22 times Vs. For reciprocal network, I double dash must be equal to I dash. Therefore, we can write G G12 equals to minus G21. That is the condition for reciprocity for inverse hybrid parameters. Let us solve a couple of numerical problems to learn how to determine reciprocity for the given electrical networks. In this problem, we have to find Z parameters for the resistive network shown. Also, we have to determine whether the network is reciprocal or not. Let the port voltages be V1 and V2 and the loop currents be I1, I2 and I3. Applying Kirchhoff's voltage law from loop 1, we can write V1 equals to 3I1 plus 2I2 minus I3. From loop 2, we get V2 equals to 2I1 plus 6I2 plus 4I3. From the third loop, we can write 0 equals to minus I1 plus 4I2 plus 13I3. From the third equation, we get I3 equals to I1 minus 4I2 divided by 13. Using this expression from equation number 1, we get V1 equals to 38 by 13 I1 plus 30 by 13 I2. From second equation, we get V2 equals to 30 by 13 I1 plus 62 by 13 I2. When we describe a two-port network using Z parameters, the linear equations used are V1 equals to Z11 I1 plus Z12 I2 and V2 equals to Z21 I1 plus Z22 I2. Comparing the expressions of V1, we get Z11 equals to 38 by 13 ohm and Z12 equals to 30 by 13 ohm. Comparing the expressions of V2, we get Z21 equals to 30 by 13 ohm and Z22 equals to 62 by 13 ohm. Now we observe that Z12 is equal to Z21, hence we can conclude that the network is reciprocal. We also observe that Z11 is not equal to Z22, therefore we can conclude that the network is not symmetrical. we have to find Z parameters for the network shown and determine whether this is a reciprocal network or not. Let the port voltages be V1 and V2 and the loop currents be I1, I2 and I3 respectively. From loop 1, applying Kirchhoff's voltage law, we can write V1 equals to 2 times I1 minus I3. The second equation we get V2 equals to 4 times I2 plus I3 minus 24 I1, and from the middle loop we can write 0 equals to minus 26 I1 plus 4 I2 plus 10 I3. From the third equation we get I3 equals to 2.6 I1 minus 0.4 I2. By using this expression from equation number 1 we get V1 equals to minus 3.2 I1 plus 0.8 I2. Using the expression of I3 from equation number 2 we get V2 equals to minus 13.6 I1 plus 2.4 I2. When we describe a two-port network using Z parameters, the linear equations used are V1 equals to Z11 I1 plus Z12 I2 and V2 equals to Z21 I1 plus Z22 I2. Comparing the expressions of V1, we get Z11 equals to minus 3.2 ohm, Z12 equals to 0.8 ohm. Comparing the expressions of V2, we get Z21 equals to minus 13.6 ohm and Z22 equals to 2.4 ohm. Now we observe that Z12 is not equal to Z21, therefore the network is not reciprocal. We also find that Z11 is not equal to Z22, therefore the network is not symmetrical either. So today we have learned that a two-port network is said to be reciprocal if the ratio of the excitation to the response is invariant to an interchange of the positions of the excitation and response in the network. Generally, networks containing passive elements like resistance, inductance, capacitance are reciprocal, and networks having dependent sources are non-reciprocal. We have learned how to derive conditions for reciprocity for different sets of parameters used to describe a two-port network. Finally, we have solved a couple of numerical problems to learn how to determine reciprocity of given electrical networks. That's all I have for you today. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.